All right, so now we're going to look at some examples that are not quite as abstract, not just a block. So we've got these two kids here, and I'm going to call them Larry and Roger. Okay, and they're pulling on this donkey. And what I would like to do is try to figure out how much force do they have to push in order to have an equilibrium condition where the donkey is not moving or it is moving. Okay, now it could be moving, it could be sliding. All right, we could have a situation where there's some kinetic friction. Okay, so we're going to look at both cases where the first case we'll look at is the donkey's actually, the boys are able to push the donkey. And then we'll say, well, what happens if the donkey isn't moving at all? How does that change the situation? Okay, so first thing that we want to do is to identify the forces on our donkey. Okay, and so we're going to have a push from back here. And we're going to assume that everything is lined up nice, horizontal and vertical. And so it's kind of an approximation because you can see over here, Larry is actually pulling at an angle, but we're going to pretend that he's pulling straight on. We'll come back to this in a little bit, and I'll show you how we could deal with it if we actually put in there the fact that it's at an angle. So our other forces that we have acting, we have the weight of the donkey, and then there's a normal force acting on the donkey. Okay, now in reality, the normal force, there's a normal force at each foot, but all of them add up together, and we're just going to work with the total normal force in this particular case. All right, so now let's move over and transfer things to our free body diagram. Okay, remember, step 1 in our recipe is identify those forces. Step 2 is we put them onto our free body diagram. So we're going to have weight here, the normal force, the force from Larry, the force from Roger, assuming they're the same. And then I forgot our friction right there, just like that. Okay. Okay. Now, this is a super easy free body diagram, and everything is nice because we have the horizontal bits and the vertical bits. There's no diagonal forces, so we don't have to worry about any kind of components in this one. So if we jump straight to our dealing with our X components, then up here in our equation, let me make it a little bit bigger. Okay, what we're going to have is we're going to have, I lost track of it. Let's call it force of Larry, it's to the left, force of Roger to the right, and then the friction is in the positive direction, and we're going to let the donkey slide. Okay, so we get minus FL minus R, FR, just like that. Okay, so we get one set of relationships that tell us that FL plus FR have to equal the kinetic friction. Okay, there we go, just like that. All right, now that's not earth shaking. Okay, and again, we're just sort of easing into how to use these tools. Okay, so we probably could have just thought about that one and gone, oh yeah, right. Okay, now let's get to the vertical information. Okay, and I want to make sure I got my picture here. Now vertically, what we have going on is we have that the normal force is up and the weight is down, and that's all we got. So our normal force is our weight in this particular case. Okay, that's often the case, but it isn't always the case. Okay, but it's often the case. All right, so let's take that information and let's put it up here into this relationship. Okay, so what we're going to have now is, make it a little bit bigger, is that FL plus Fr is Fk, but Fk is mu k times the normal force. And we found the normal force is the same as the weight. So we have mu k mg. Okay? All right, now if we plug in all of the numbers that we were given for mu, for the mass, then what we're going to end up with is that FL plus FR has to be equal to 858. Okay, now let me zoom back out a little bit on this. So that's the relationship that we have there. Okay. Now that would be where the donkey is sliding. Okay. Now I want to compare that to if the donkey was holding still. Okay. Now if the donkey is holding still, then I need a different color. Then everything's the same except we have to change this equation. Okay, we've got to change that equation right there, because for static friction, we have to say it's less than or equal to the static coefficient times the normal force. Okay, so one difference it's a really important difference, but one difference between this dealing with static friction and kinetic friction is kinetic friction, it's moving, but with kinetic friction, you know 100% the value of the friction force. With static friction, you don't know what it is. All by itself, mu times n doesn't give you enough information. Okay? And so if we run the math with our mu sub s, okay, what we get here is that it's 1100. Okay, so that means the donkey is going to be in equilibrium as long as the boys don't push more than 1100 newtons. Okay, if they push more than 1100 newtons, then the donkey's not in equilibrium anymore. Okay, so the static friction only does what it has to do. Okay, it's not going to do any bit more. So we have to think about it like this. So here's this object, and let's say it's sitting on a surface or something here. All right, and my static friction could produce, let's say, 100 newtons of force. Okay, so if I push with 10, the static friction could go up to 100. It only needs to do 10. It will only do 10. If I push with 70, it will only do 70. If I push with 99, it will only do 99. If I push with 100, it'll do 100. If I push with 101, it's going to move. Okay, so that makes dealing with static equilibrium with involving static friction can be a little bit tricky. Okay, because we don't always know what it is. All right. Okay, let me zoom out so you can see here. Okay, and again, one more time with our recipe, we want to identify the forces on our figure, make our free body diagram. Okay, break down the horizontal and the vertical forces, and then do our algebra. Okay, now I know this is a little bit overkill here, but okay, so 1, 2, 3, 4. Okay, so I hope that makes sense. Okay, algebra at the very end. Okay, so here's a little pug. Okay, and let's zoom in on our pug here. And this little girl is trying to pull the pug. And let's suppose that, just to make the physics and the math easier, let's suppose that the pug is actually sliding. Okay, so the pug is sliding, and there's a coefficient of kinetic friction there. And we want to know what has to be the tension in the rope. Okay, so let's come over here. So we got some tension here pulling on the little pug. All right, now that tension is sitting in there at some angle. And let's just suppose that that angle is 20 degrees, okay? Just like that, all right? 20 degrees. And let's think about the other forces, okay? So obviously there's going to be some kinetic friction here, obviously some weight, and obviously a normal force so that the pug doesn't fall straight through the concrete. Okay. All right. So now that was step one. We identified our forces. And so now let's put them onto our free body diagram. Okay. And so we've got our tension here and our weight, our normal force, and our friction, like so. Okay. We know that angle's 20 degrees. Okay, now, so let's slap some labels on here. Just like so. Now we know that we're going to have to deal with components. So let's get our TX and let's get our TY. Just like that. Okay. All right, so there is step 2 in our recipe. Let's move, then begin step 3. We got to put all these pieces together. So if we look horizontally, I've got my friction to the left, and I've got TX to the right. There you go. And let's move to the vertical information. Now I've got N is up, the weight is down, but I also have this thing here, TY. Okay, so now I've completed step 3. I've written down my horizontal and my vertical force relationships. So let's dig in with this thing. Here, use white. So we can see that Tx is going to have to be equal to the friction. Okay, and this is kinetic friction. So we're going to have mu k times the normal force. All right. Okay, now we got to figure out what we have for the normal force, and it's a little bit different this time because our normal force is equal to the weight minus Ty. Okay, so our weight is not just mg. The weight is just mg. The normal force is not just mg, and it's actually less. Okay, and you can see here the girl is pulling. So she's pulling up just a little bit, which means the normal force doesn't have to exert as much effort as it did before. Okay. So here's an example where you don't want to just assume that your normal force is always equal to the weight. Okay. Now let's take this guy and plug it in up here. See what we get, and what we're going to have here is Tx is equal to mu k onto W minus Ty. Okay. Now I apologize, this is going to get just a little bit messy. There's no way around that here. But what I want to do now is I want to use what I know about Tx and about Ty, which is to say that Tx is T cosine theta. And we know theta is 20 degrees. And that's mu k onto W minus T sine theta. Okay. Aha! Now check this out. So now I don't know T. That's the only thing we don't know. We know everything else. Okay, just like that. So at this point, it's an algebra problem. And so let me just do that pretty quickly here for you. Get back to my pink. Okay, so I've got T. I'm going to bring my T to both sides, which is going to leave me with cosine theta plus mu k sine theta. And that's going to be equal to mu k mg, where W is is mg, of course, just like that. So my tension then is going to become mu k mg over cosine theta plus mu k sine theta. Okay, then all I have to do is I just got to plug my numbers in, and then I'm good to go. Okay, and if you run the numbers on this one, what you actually get is like 77.1. Okay, just like that. Okay, let me zoom out. Get a bird's eye view here. Okay, again, identify your forces on your diagram, make your free body diagram, get your horizontal and your vertical forces going, and then do your algebra. Okay, so let's do another one. Okay, now this one I'm just going to set up. Okay, we're not going to go very far on it, because now what we're going to do is we're going to allow for Larry. Remember, Larry was over here. Roger's back here. We're going to allow for Larry to be pulling down. And Roger's still pulling here. Still have our normal force. Still have our friction. And we still have our weight. Okay. Now, when we put those on to our diagram, okay, I've got a normal force. Got Roger. But Larry is pulling down here at an angle. And then we've got our normal force, just like this, and then our friction back here. So normal and friction. Okay. Now, Larry's force, we're going to have to deal with components. We're going to have an LX and an LY. Okay, so we come up here, and we're going to have, I'm just going to call those forces L and R. So I've got R to the left, and and then L, but we have the X component of Larry's effort. Okay, and then plus the friction is equal to 0. And it doesn't, I don't care if we're doing static or dynamic at this point. I just want to show you what happens. Now let's look at, in the vertical direction, we've got N is up. The weight is down. That's weight, by the way. And then we also have a Y component for L. Just like that. And so you can see what's going to happen here. If I look at my normal force in this case is actually greater than it was before. Okay. And so there's kind of a lesson here. All right. So if you're pulling on something, if you pull down, what happens is you actually cause the ground to have to do more effort. So you got a larger normal force from the ground. Okay. So that means whatever you're pulling and the ground are squeezed more tightly together. And when you do that, you're going to affect the friction. Okay. So in this case, we increased the normal force, which means we've actually increased the friction. Whereas with the pug in the last picture, we decreased the normal force, which actually decreased the friction for us. Okay. So this is why if you've got some furniture, okay, so let me try to draw, I need something, big space here. Okay, let's suppose you got a big crate here. All right, and you want to push this crate. So I'm here pushing on this crate. Not very happy. Okay, I'm not very happy because I'm pushing downward like this. And that downward effort is going to increase the normal force, which means that I'm increasing my friction. Okay, so that's not cool. It works much better. And if you've ever moved furniture, you know this. It actually works much better to get on the other side like this and pull. Okay, so if you got a big couch or something, you probably know from experience that if you pull that couch across the floor, it's easier than if you try to push it. Now you know why. When you pull it, you're reducing the normal force, which eventually reduces the friction. But if you're pushing on that thing, you increase the normal force, and then that's going to increase your friction, making it a lot harder. Okay? All right, so there's the end of part 2. We're going to cut that thing off before it grows too big and out of control.